Group 5 chose to explore the Raft consensus algorithm and compare it to two of its alternative consensus-forming algorithms. A consensus-forming algorithm is an algorithm that can coordinate a series of machines in a network in order to form a unified log of the state of the network. These distributed consensus algorithms have a wide breadth of applications that encompass everything from bank logs to distributed file systems. Let's explore how Raft works. Here is a key to all the elements represented in the animation. First, the machine boots and all nodes come online. Then the election process begins. All nodes send out votes for the new leader. Once a new leader is chosen, it sends out a heartbeat to let the other nodes know it's still alive. When a value needs to be updated, it is sent to any node, which is then forwarded to the leader. The leader sends this new value out. Then the leader dies and the election process starts over. The new leader will then send out its own heartbeat. The first alternative to Raft is the Ripple consensus algorithm. Despite both Ripple and Raft controlling a common log across a network, they vary widely in the methods used to maintain that log. Ripple utilizes an iterative voting process to ensure changes to a log are common throughout a network before they are applied to the log. In contrast, Raft votes for a leader node, which then dictates what is in the log, and the other nodes simply replicate it. This means that Raft is heavily dependent on each node of a network, trusting the other nodes in the network, while Ripple is dependent on each node being skeptical of the other nodes. This major difference begins to show how these two algorithms can be applied to very different distributed networks. The major benefit of the Raft algorithm is in its simplicity of implementation compared to Ripple. However, Ripple is more resilient to rogue nodes and attempts at disrupting the network's operation. It also has a more robust 80% required agreement between nodes in order to reach consensus. Unfortunately, this higher percentage of agreement can quickly become more time-consuming than Raft's simple majority, due to multiple voting iterations being required for the higher level of consensus. These differences allow Raft and Ripple to suit the needs of very different application spaces despite their common goal of log consistency. A couple of examples of these varying applications are Ripple's use for accounting, ledger control, and Raft's use in distributed operating systems. The second alternative to Raft is Paxos, which is the original consensus algorithm. While Paxos and Raft have many similarities, there are a few major differences. Paxos is designed around the theory and mechanics needed to keep consensus between systems, while Raft was designed around practical implementations of distributed systems. Raft is much easier to understand and implement. One of the major differences between the two is their leader elections. Raft requires one leader before allowing any changes to the log to propagate to the rest of the nodes in the system, while Paxos can have many nodes that believe they are the leader, but the leader is only chosen when a proposal is accepted. Leaders in Paxos also have much less relevance versus Raft. Paxos uses node quorums, which are subsets of nodes within a system that can have their own consensus. Paxos is important mainly because of its historical relevance. First published in 1988, it was the first such algorithm to offer a proof of safety aka correctness, for the niche of distributed fault-tolerant systems. A major motivation for the creation of the Raft consensus algorithm is that Paxos is very hard to conceptualize and implement. So the creators wanted something that was more intuitive and understandable. This made Raft significantly easier to implement in practical systems, as they designed the algorithm with that in mind. Since Raft is functionally equivalent to Paxos, there is not much of a reason to use Paxos today. In summary, the Raft consensus algorithm was developed to replace the academically complex Paxos algorithm with a simpler and more intuitive implementation for a similar process. It is more generalized yet more efficient overall, which is the reason for the adoption and popularity of Raft.